Okay, I want to take a look at this idea of hypothesis testing and something called a type 1 error and a type 2 error in the context of classical testing and PROB value testing. So let's start with this, this information that we've got here, where we've got, let's say, 1,000 people accused of a crime, and careful study after the fact discovered that 3% of the truly innocent people were wrongly found guilty and 9% of the truly guilty people were wrongly found innocent. So what does this mean? So if we just think about it this way, we've got 1,000 people. That means, let's say over here, we've got 60%. That's 600 people over here. We've got 1,000 people in total. So this is the 1,000 people in total. And this side over here, the 600, are the ones, that's 60%. These are the guilty people over here, or at least found were in fact guilty. And then we've got, that means 400 people over here on this side. These are the people that were in fact innocent. But then it says that 3% of the truly innocent people were wrongly found guilty by the courts. So these are the 400 truly innocent people over here, and 3% of them were wrongly found guilty. That would be this group over here, 12 people. And then it says 9% of the truly guilty. The truly guilty are the 600, and 9% of them, that would be, like, say, 54 people here. So that means of the 400 that are innocent, 388 were found correctly innocent. And of the 600, 546 were correctly found guilty. But we can see now that 54 plus 12, 66 people in total, 66 of the 1,000, that's 6.6%, were, well, there was an error. The court came to the wrong decision. But you can quickly see here that the 54, the 12, it's two different mistakes. It's one thing to send an innocent person to prison. It's another thing to let a guilty person go free. And the difference between these mistakes is what amounts to what is called a type 1 error and a type 2 error. They're not the same. Sending an innocent person to prison, letting a guilty person go free, while both mistakes, they're somehow different. So I want to take a look at this idea a little bit more. Statistically, we say that type 1 error means to incorrectly reject the null hypothesis. Think for a second, in a criminal trial, the null hypothesis is that the person, you're presumed innocent until found guilty. So type 1 error means to incorrectly reject the null hypothesis. That's the case of sending an innocent person to prison. Type 2 error is the failure to reject a false null hypothesis. And that's the equivalent of letting a guilty person go free. So the fact 1 is the type 1 error. The fact 2 above is like a type 2 error. In statistical terms, and we'll come back to this again, the probability of type 1 error is called alpha. It's referred to as the significance level, or in a PROB value sense, it's the PROB value. We also will later look at this idea of confidence, and the confidence level is equal to 1 minus alpha. This is notation. The probability of a type 2 error is known as beta, and the term that's used for this, the power of the test, is 1 minus beta. Again, we'll come back to this. It requires a null hypothesis, an alternative hypothesis. Let's take a look at this in the context of a chi-squared test. Remember that the null hypothesis is like you're wasting your time. The innocent person should never have been arrested. There's no reason to have this person. There's no connection between the variables. In the chi-squared sense, it's the observed frequency, or the observed table, and the theoretical table are similar. So we can say that if you set up a significance level, let's say alpha 5%, then the white area on the right there is alpha, and we can look up in the table to find the critical chi-squared, and then we say if it's to the left, we accept the null hypothesis, or more likely fail to reject. This is like finding a person innocent. And actually, in a court of law, they don't say we find the person, they say we find the person not guilty. If, on the other hand, the chi-squared statistic that you calculate from the data is to the right, that's greater than the critical number that found in the table, then we say that you reject the null hypothesis. In a court of law, we'd say the person is guilty. So we reject the null hypothesis. If we had an alternative hypothesis, let's say, for example, the variables are connected, or the person is guilty, or in this case, the data sets F observed and F technical, theoretical are different, then we have an alternative hypothesis, and we can say then that, well, we rejected means we're to the right of the critical number from the table. But you'll notice something. It's possible that we reject the null hypothesis when it's true. So when I draw the curve on the top, it's working under the assumption that the null hypothesis is true. And there's a possibility of making a mistake. That's rejecting the null hypothesis, committing a type 1 error. And the chance of doing that is alpha. I said 5%. Of course, we could minimize that risk by making alpha smaller. So the white area represents the chance of making a mistake. In the same sense, we could accept the null hypothesis when it's false. And that would be beta. Because in effect, the alternative hypothesis is true, and we mistakenly accept the null hypothesis. So in both these cases, the white area is the chance of committing alpha, type 1 error, beta, type 2 error. The confidence level is 1 minus alpha. That means we've correctly made the decision. And if the null alternative hypothesis is true, and we reject the null hypothesis, meaning we accept the chance of doing that as 1 minus beta. That's why it's referred to as the power of the test. I want to take a quick glance at this idea of alpha because it's arbitrary. In the context of criminal proceeding, or rather legal proceedings, think of alpha here as being, say, I've just made up these numbers arbitrarily, but imagine this is alpha 25%. That means to say there's a relatively high chance that we're making a mistake in rejecting the null hypothesis. For the police to make a search of a person, they have to have reasonable suspicion. That means you're walking down the street, they may possibly make a mistake. You're not doing anything wrong. So the danger of making a type 1 error is not too serious. Move down to a criminal trial beyond a reasonable doubt. Well, then we'd say alpha now is equal to 1%. So that the chance of, in effect, sending an innocent person to prison, which would be a serious mistake, that's a serious type 1 error, we reduce it by moving, if you will, the critical chi-squared from the table before, move it far to the right, so the alpha, that white area, becomes smaller. Just a note here that criminal trials are ones in which the state or the crown accuses somebody, and then the danger is that, the person could go to prison. In a civil suit, it's just between private individuals, and then it's just money. So, for example, most civil cases have a lower standard. You just imagine the alpha over here in a civil case, the balance of probabilities, clear and convincing evidence. These are not as strict or as strong as beyond a reasonable doubt. Another one that's interesting is for the police to accuse somebody, they have to have what's called probable cause. That's a relatively weak standard. You can sort of say alpha is equal to 20%. As I say, I invented these terms. And further, the 25, 20% for alpha and so on. Something else, too, is that I took these definitions in part from Wikipedia and from other sources. So I think these are really the terms that are used in the United States. Some of them are used in Canada as too. But you can clearly see that some of the standards are greater than others. And there's a direct connection here between these definitions of reasonable suspicion, 25%, and alpha, and so on and so forth. I want to finish with this idea here of this chart, if I will, that really illustrates this well. You can imagine the situation up here. We accept the null hypothesis, and the null hypothesis is true. That means we're making a correct decision. The chance of doing that is 1 minus alpha. That's the confidence level. And in effect, what it means is the innocent person goes free. Look down here at the bottom. This is another correct decision. This is where we send the null hypothesis false, the person is not innocent, and we reject the null hypothesis correctly. So in effect, we send the criminal to jail. The chance of doing this is 1 minus beta. I'm going to pay particular attention to the ones in the top because this is what we do in the course more often, is just having alternative hypothesis can sometimes be, well, there's many of them. Court trial is simply the person's found guilty or innocent, but in social science research there could be many others. But take a look at this case up here. This is where we make a mistake. This is a type 1 error. This is also known as a false positive. That means to say we send an innocent person to prison. So the null hypothesis is true, but we reject it mistakenly. In a medical sense, a false positive would be, again, the null hypothesis in medical sense is the person is not infected, they're disease-free, there's no problem. A false positive is when you go for, say, some kind of a test, and the doctor thinks that you are ill when you're not. So they reject the null hypothesis when it in fact is true. So we refer to that as a false positive. You can imagine this is bad for the person because they may think that they're infected with some disease when they're not, actually, in fact. The other possibility, of course, is this one down here, wrong decision, type 2 error. The chance of doing that is beta, but this is known as a false negative. Criminally, this would be a criminal goes free when they should be going to prison. In a medical sense, it's very dangerous as well because you're telling a person who is ill, who is infected, that they're not infected. So you can see that you'd want to minimize, and this is typically what they do for medical tests, is that the alpha is actually quite high, so there's a relatively high chance of committing a false positive. But then if it's tested positive, they send the person for a further test, which means that you minimize the chance of a false negative. If you could just go back for a second to this previous graph, you can quickly imagine that if we moved this whole line here further over here, we would reduce the chance of a type 1 error, making this white area here much smaller. Alpha then would become very small. But of course, in the process of doing that, we'd make beta much larger, which means we'd be risking the chance of committing a type 2 error. So it's a bit like saying there's no chance of ever sending an innocent person to prison if we find everybody not guilty. So frequently, some tests, the alpha is quite to the left initially when the test is not very expensive, and then when the test becomes more expensive, they move the alpha further to the right, which is what happens in a criminal trial. For the police to stop and search somebody, the cost is not that high, and so there's a relatively high chance of committing a type 1 error. But then when it comes to the court case where they're actually going to send the person to prison, then we move this critical line further to the right and reduce the chance of committing a type 1 error. Okay, last, I want to look at this idea of a PROB value, because here the order is a little bit different. We assume that the null hypothesis is true. I mean, go back to the example of chi-squared. The two tables are similar. There's no connection between variables, or the person is innocent, or the patient is not infected or doesn't have the disease. In this case, we initially calculate the chi-squared from the table, or if, for example, you go to a medical test of some sort, they assume that you're disease-free, you're normal, and then based on the number that's calculated, that the data gives you, you then determine the white area. So alpha is not determined in advance. We calculate a p-value instead. Of course, we have to determine the degrees of freedom in the case of the chi-squared or whatever, and then the PROB value, the p-value, is reported in the data, and so it's left to the researcher or the person reading the article to determine whether or not they will agree or not agree with the null hypothesis. This kind of approach is good for research, even medical research, but it's not very useful in a court trial, and it's not very useful for a doctor treating a patient. In a court case, they have to come up to a decision about whether the person's innocent or guilty. They couldn't simply report the p-value and then say, well, it's up to society to decide what to do. Same with a patient in front of a medical doctor. The medical doctor has to make a decision about what treatment to pursue. simply saying what the p-value is not going to be helpful. But for research, this is frequently it's done. Bear in mind, p-value is the white area, assuming the null hypothesis is true. So you could imagine that if p-value is, of course, the p-value varies between 0 and 1. If it's very, very close to 0, then you'd say that it's very unlikely that the null hypothesis is true. On the other hand, if p-value is close to 1, then it's very, very likely that the null is true.